Okay. All right. Hello, everybody. Sorry, I had a meeting right before now and it took longer. So I know that a couple of you emailed me about the dilution question. So we'll go over it together. And if you have more questions, we can talk after class. So yeah, you can stay a little bit. My glasses are foggy and yeah, there we go. Okay, so let's get started. I told you guys to give it a go. So what can anybody share? Who is your approach? Even if you're not confident with the approach, that's okay. Okay, Lenny? Two liters? Yeah. Okay. Okay, so you're on the right track. So what you want to do first is unify the units. So remember that your units have to be the same. So when we say, okay, so when we say 16%, what does that mean? That means 16 grams in 100 ml. So the first thing you want to do is change your unit to milligrams per milliliter. So that's the first thing you want to do. So now you have grams per 100 ml. So if I want to say grams per milliliter, so I divide by 100 both places, so it would be 0.1, 16 grams per 1 ml. Okay, I need to convert now grams to milligrams. So I'll multiply by 1,000. So I'm converting grams to milligrams. So I multiply by 1,000. So now I have 160 milligrams per milliliter. So that is your stock solution concentration. You apply your concentration by volume, equal concentration by volume. So you want 2 milliliters, your final volume. And you want, okay, for 0, it will be just 2 milliliters of water. 4.1, so you want to say, okay, I want to pair 2 milliliters of 0.1 milligrams per 1 ml concentration. And my stock solution is 160 milligrams per milliliter. How much do I need to get this concentration and this much volume? So when you solve for X milliliter, it was 0.00125 milliliters. Oh boy, such a tiny volume. If I want to convert this to microliters, so move it 3 places, multiply by 1,000, it will be 1.25 microliters. I don't have a pipette in the lab that can accurately and precisely dispense 1.25 microliters. That is next to impossible. So I just go, okay, my stock solution is too concentrated. I want to make my volume at the end reasonable that I can pipette. I would say, I can tell you, you don't want a decimal of a microliter. You do not want 0.5 microliter, 1.25. You don't want that. You can't handle that in our lab or in any particular lab. So what you want to say, okay, I'm comfortable working with 125 microliters. So I want to make this 100 times more. You can do that. We have 200 microliter pipettes. So you can dispense 125 microliters. But if I take 125 microliters, this is going to be 100 times more concentrated than I want it to be. So what you do in this case, you dilute your stock solution. So you dilute the stock solution by 100 times. So I have my stock solution that has 160 milligrams. So in order for it to be diluted by 100 times, say how much volume do I really need? Small amount. So if I prepare like only very little amount, let's say, okay, I want to prepare 10 ml of my diluted solution. I can do that. So I can prepare 10 ml. So if I want to prepare 10 ml of that, 10 ml of what do I want it to be 100 times? I want 1.6 milligrams per milliliter. Okay, so I want to prepare 10 ml of 1.6 milligram per milliliter. That's 100 times less concentrated. And so I have 160 milligrams per milliliter. How much do I take out of that? Okay, so I would say 16 divided by 160. So I would take 1.1 milliliter. So I would take 0.1 milliliter of this stock solution, so our 100 microliters. 0.1 milliliter equal to 100 microliters. Because you multiply by 1,000. And then I would place that with 9.9 milliliter DDW, distilled water. So I would pipette 100 microliter, which is equivalent to 0.1 ml. To make 10 ml, I add 9.9 milliliter. I now have a diluted stock solution. From there, I use this stock solution now. Instead of saying 160, now it's 1.6, and I solve for my x. So that's how you do it. Okay, so the first thing you do is convert percentage to milligrams per 100 ml. And then from milligrams to per milliliter, which is the same unit. So the first thing you do is convert the units. And then you follow concentration times volume equal concentration times volume. And you come up with this very, very, very small volume, and it's 1.25 microliter. You don't want a fraction of a microliter, you already know. I'm like, okay, this is too small. So I dilute the stock solution 100 times, and the calculation is here. So 0.1 ml in 10 ml. And then you take, you put it with water, and then you get this concentration of 1.6 milligrams per milliliter. And then you apply C times V equals C times V. So you get the 125 microliters instead of 1.25 microliters. And then you add this to 1.875 milliliter of water. You get 2 ml with that concentration. And you do the same calculations for 0.2, 0.3, and 0.5. Any questions?
Can you just show on the board which step is the stock solution over the time?
This, okay, this one. Yeah. So I decided that I don't need a lot. I don't need a liter. I can just work with small volume because at the end of the day, I only need a few microliters. So 100 times diluted from 160 milligrams to milliliter, 100 times dilution is 1.6 milligrams per milliliter. How much I take of that is just following this equation, and it tells you, okay, I need 0.1 ml, 100 microliters. I add that to 9.9 milliliters of water. Okay. Any other questions? It's okay to ask. Don't be shy. I'm happy to repeat. There will be dilution problems for next week's lab. You want to be comfortable in calculations. The pre-lab quiz will have a example calculation, or not example, question for calculation, and also answering the questions of the lab report will include calculations. So if you are unclear about anything, I'm happy to repeat. Any? What's that? A double distilled water. Usually in the lab, we want to move minerals from the water. So we distill it and sometimes we double distill it.
Your PowerPoint demo.
No, take a picture if you want. I only post online without the calculations. Yeah, I'll let you take a picture if you want. Okay. I'm waiting, folks are taking pictures. All right, as long as I'm not in the picture. Okay, good. So I'm going to start talking about moving on to buffers. So you will be preparing a buffer next week in the lab, and it's really important that you know how to prepare a buffer. And I didn't have that part in food analysis. There's no chapter in your textbook about preparing buffers. I believe there might be in the manual that's in the new edition. So I didn't go over that. A few years ago, I didn't go over buffer preparation. And then it hit me one time when one of my graduate students was preparing buffers for several years as a graduate student. And after 2 or 3 years, I figured out she was doing the calculations wrong. And, you know, it impacted a lot of data. So I realized that, you know, students at an undergraduate level, if they don't get this information, there's probably nowhere else to get that information. So I thought it would be good to have that here so that you, when you're doing your research or even working in industry, you know how to get the buffer, prepare a buffer. Now there's also online, there are calculators for buffers, which makes life a lot easier. But it's good to know how the science behind it. Okay, so buffers consist mixtures of weak acid and their corresponding bases. We call them either salts, conjugate salt, or conjugate base. So that means the acid with the hydrogen dissociated. So that the proton is dissociated. So the weak acid is the acid with the proton, and the conjugate base is when the acid loses its proton. Okay, it stabilizes a certain pH of the solution for a particular reaction. So it stabilizes the pH. And the main principle here is that the solution resists change in pH. So if there is a reaction that happens, let's say breaking down of peptide bond, you release carboxyl groups, the pH drops. But if you want to maintain the pH of an enzymatic reaction at its optimum, you must have a buffer that resists that change in pH. So when you have, and the buffer should have a weak acid and it's solved in the same medium. And this equation is kind of a key equation for preparing buffers. What does pKa mean? Let's remember our general chemistry a little bit. So what is pKa? Okay, Abi. What's that?
Dissociation constant for acidic.
Dissociation constant is your Ka. What is pKa? Okay. Nobody, I'm sure you know it. You just don't want to say it. Okay, it's very simple, and you can derive it from this looking just at the equation. It's the pH at which you have equal concentration of acid and its conjugate base. So if you look at the log, if you have equal concentration of the conjugate base and the conjugate and the acid, the log becomes 0. So log of 1 is 0. So it's the pH at which you have equal concentration. That's maximum buffering capacity. So like I said last time, when let's say we're titrating and we're titrating with NaOH and there is a buffer or a buffer, like a weak acid that is buffering. I'm titrating with OH, NaOH, this proton is going to be lost. If I'm titrating with HCl acid, this guy over here, the conjugate base, is going to pick up the acid, and then the pH is maintained. When we have same concentration here and here, you have maximum buffering capacity. And that's when pH equals pKa. All right. So we'll go through this step by step together. But I want you to take a minute or two, just think about it and see how would you approach this exercise. What I want to know is how would you approach it? I'm not waiting for an answer from you, but what would be your approach? So give it a minute or two, and then we can start solving it together. And when you have an approach or a start of an approach, let me know, raise your hand. Yes, Brittany.
So I think the first step would be to figure out the molarity of the sodium acetate powder.
Yes, that would be a good first step. Is you have a powder and you want to prepare a solution of your sodium acetate powder. So it's in a powder form. So you need to have it in a solution that will ultimately contribute to a 1 molar solution of a buffer. So that is a first good approach. What else we want to do? Yes, Paige.
So you want to change the Ka into pKa?
Absolutely. So if you want your scientific calculator to convert your Ka, which is the coefficient of dissociation that Abby told us about for acid, and we want to convert it to pKa, that's good. So 2 good approaches. What else do we want to do? This is all with our given so far. Your acetic acid is in 3 molar. So what do we want to do there? Dilute. Yes, we want to dilute it. Yeah. Okay, so there are 2 approaches to solving this problem. There is an approach that is common And then there is an approach that I like better. So, so the first thing you want to know, remember, is you want to get the 1 molar solution at the end. So I will show you the common one that people utilize, and then I will show you the one that I prefer. So the first one is, first of all, you have the equation, the Henderson-Hasselbalch equation. So which says pH equal pKa plus log of conjugate base concentration over acid concentration. I want to say this can be a concentration in molarity. It can also be volume, not concentration. It could be volume of the conjugate base over the volume of the acid. So I want to prepare 1 liter of 1 molar. If I want to solve to determine what concentration I want of my base and what concentration I want of my acid, the first thing I want to put here so that I can unify and solve for X instead of X and Y, I would say, okay, concentration of A plus concentration of HA equals what in my final buffer? What's the final concentration of the buffer? 1. So equal 1 mole per liter or 1 molar. Okay, so if I want to solve for A minus, then I would say, HA, because I'm going to replace this with A minus. So I would say HA equals 1 minus this. And I can replace this by that, and I can solve for A minus concentration. So I would just say pH equals pKa plus log A minus over HA. Oh, sorry, over 1 minus okay. So now I can solve for A minus. So first of all, I have a pH of 4.6 equals pKa. What is the pKa based on your calculator now? 4.76. Okay. Equal, no, plus log of A minus why do I keep messing up here? Okay. So I want to get this value then. 4.6, not 7.6, right? Okay. So can you figure that out in your calculator? What do you get? If I want you to give me the ratio of this, what would it be? After you solve and get the log, so what would be this value? With your scientific calculator, try it out. You want to learn how to do that because if I ask you a question in the quiz or exam, you want to be able to know how to use your scientific calculator. And if you don't know, you got to find somebody that knows and tell you. Yes? Yeah. Yeah, what is the value?
10 raised to negative
10 to the what? No. There must be something with how you use your calculator, Sandy.
I got 0.69.
Yes, that is the value. 0.69. So, you want to figure out how to use your. Okay. All right. So you get 0.69. If you don't know how to use your calculator, ask a friend. But it should be simple. Every calculator will be different. So you should have to just figure out so that you can get this value. So when you get this value, then you can solve for conjugate base. And this value in here, I'm going to call it concentration in molarity or moles per liter. Okay, then what is your A minus concentration after you solve that? Algebra. So 0.69 minus 0.69 A minus. How do I get 0.69? Is you solve for here. So you bring this number here, so it will be minus 0.16, right? And then on your calculator, you want to get the log, anti-log, I guess. So then you can get that value here. It's just a matter of using your calculator. Every calculator is different. You just have to figure which buttons on your calculator you need to press to get that number.
Negative 0.16. That's why we spend. So
Yeah. So yeah, but some calculators are different, so you can figure it out. Did you figure it out? Yeah. Okay. All right. So what's the A minus concentration that you get, Michael?
I have a total answer of 0.408.
That is a good answer. That's a confident answer.
Nope.
And then so now I have my conjugate base and I have here this equation, and then the concentration of the acid is 1 minus this. So the concentration of my acid is, what is it?
590.
Right. Okay then, but the problem is not solved yet. I know that on my liter, in my final liter, I need this much of conjugate base and this much of acid. How do I get this and how do I get this from a 3 molar and a powder? Let's solve the acid situation, the base situation first, which is the salt. Conjugate base, sodium acetate powder. I have molecular weight of 82 grams per mole. How much do I need to weigh to get this much? So what is your approach there? What equation do you want to apply? All right. Go ahead, Sandy. Yeah, which is, we know that molarity equals number of moles over volume. And usually it's in liter. And normality is moles per gram. Number of moles per, it's just moles per liter. Okay, and then number of moles equals mass in gram over molecular weight in grams per mole. So I have 0.408 molar, that means 0.408 moles. So I have this value. And then I have the molecular weight, which is 82 grams per mole. Then I can calculate how much I need to weigh. So what would be the mass in this case? Who did the math? So number of moles equals this, because this is in a liter. So in a liter, how much do I need to weigh to get this molarity, which is number of moles per liter? And Drew? 33.5 grams. I want 33.5 grams of my sodium acetate in a liter. Great. So I know how much I need of sodium acetate. Now, how much do I need of this? How do I calculate? So for the acids, I have a solution. So I have a 3 molar solution. How much of that I need to prepare 1 liter of 1 molar? Okay. So what would be? Oh, sorry. Hold on. This. Not 1 molar. I'm sorry. I'm sorry if I confused you. I need this concentration of the acid. This is the concentration of the base. We figured it out. This is the concentration of the acid. So 0.592 molar. So that's the equation I need to solve to get how much I need of my acid. Is this one clear? Drew?
Oh, no.
Who has the answer? Yes, hold on a sec. Is this clear that we have a 3 molar solution? I only need 0.592. So how much do I need from that concentrated solution to get the 0.592? And where does the 0.592 come from? From here. It is 1 minus the concentration of the base, which is this, because I want to end up with the 1 mole. Okay, so what is your answer? 100?
It's 1,000 milliliters.
Yeah, 197, you said?
Yeah.
Yeah, correct.
I just added.
Okay, 197 milliliters. Okay, so now, how do I physically prepare that? I get my volumetric flask. And then I put 190, well, I try to put first some water. And I will put my acid in there. And if I follow proper laboratory techniques, I'll get a small beaker and a little bit of water, maybe 200 milliliters water, 100 milliliter water, whatever, a small amount of water. And I weigh this in here. So I weigh and I put my sample in here. Then I add a little bit of water, 200, 100, 150, whatever that will help dissolve this. So I dissolve it, I stir. I get my 33.5 grams already dissolved. I have some water here with the 197. I add this here, and I make up to volume with dVW. And now I have my 1 molar buffer at pH 4.6 and 1 mole. Now you prepared it. That's not the end of it. You'll see in the lab next week that when you prepare your buffer, make it up to volume and you have everything in there, you need to measure the actual pH. You are actually preparing the buffer, assuming that with all of these calculations, you should get a 4.6 pH. Sometimes it's not the case. It's not exact. So you would just have to put a pH meter in, measure, and adjust with acid or base. Yeah. The molarity. How I got the 0.408.
Basically, how you got the
Which one? Here or here? There? Oh, okay. So did you get how we got this molarity? All right. So this is the concentration of your conjugate base. And your conjugate base is sodium acetate. And here I'm telling you it's a powder. So you want to weigh out a certain amount that will give you this concentration in a liter. Okay, so how do I know how much to take out of this powder so that I can get this concentration in 1 liter? So I remember from my chemistry that molarity equals number of moles over volume. And the volume in this case is 1 liter. So my number of moles here is 0.408 moles per liter. And then I have the molecular weight, which is given 82 grams. So I'm solving for mass. I have number of moles, 408 moles. I have my molecular weight, which is 82 grams per mole. Units cancel, and I get mass in grams. And here's my mass. So I need to prepare it in a little bit of water to dissolve it. And now I know how much acid I need. I take my volumetric flask, add some water, acid, add my salt that is dissolved, make up the volume, shake, measure pH. pH is not 4.6, often happens. You adjust the pH with a concentrated acid or a concentrated base. You'll be doing that in the lab next week.
I also have another question. I'm probably just overthinking it, but when you did like the times 1,000 millimeters, like because I realized you did that because it's 1 liter, but like if you're, I guess like it's like 0.592, so you still have to account for the other. I guess like why did you choose 1,000 millimeters?
I want to prepare a liquid.
Right, even though you have to account for the other. Like what if
Yeah, so the
what if
other,
it's 2
yeah,
liters?
you want in this 1 liter, you want this concentration. Because this is the concentration of the acid in 1 liter. So this is molarity, so constant moles per liter. So this is your liter. So you need 197 milliliter of the acid. It gives you this much moles. And you put them in a liter, you get this molarity.
So even if like the conjugate base was a liquid, you would also use 1,000 millimeters.
Yeah, you're adding both of them together to get to 1,000. So the final volume is 1,000 for both of them. That's a good question. The final volume for both of them is a liter. So for both of them, you have to put that 1,000 liter at the end. Okay. Oh, it was a random volume. In lab, in practicality, you have to powder. You have to dissolve the powder before you add it into the volume. It's 3, doesn't have to be. No, it can be 100. It depends. I don't know what the solubility saturation of this thing is. So I just randomly said a little bit of water, 100, 150, 200, doesn't matter. Just make sure it's soluble, it's in solution before you put it in your volume. Okay, so the way I like to do it is, okay, you want to take a picture of this? Take a picture of this. This is exactly what I explained here. Say plant proteins. Yes. We are very obsessed. We dream, we eat, we talk, plant proteins. That's the way it goes. All right, are we good? You took a picture? All right, let's talk about how I would solve it. I'm gonna keep some of this. All right, I will show you another method and then you remember whatever you're comfortable to remember. Both are correct. All right, in my method, or not my method, make it up. In the method I like to use, I would say, I want to make a liter. So I would say, this is going to be equal. I'm going to take this in liter or milliliter. Instead of a concentration, I'm going to use them as a volume and say I want to prepare, or milliliter for each. I want to prepare 100 milliliter of this buffer and the 1000, sorry, 1000 milliliter, which is a liter. So this would be 1000 minus the volume, in this case, of A minus. So the first thing I would do if I want to use volume in this equation is I want to prepare a 1 molar solution of acetic acid and 1 molar solution of the base. So I would go and prepare a 1 molar solution of acid, 1 molar solution of base. So now, when I mix them, they're both at 1 molar solution. So what I would say then, I want to prepare a 1 molar solution of the acid, and I'm going to prepare a liter of it. I just decided I want 3. And then I have 3 molar, that's my stock solution. I have 3 molar acetic acid, so I'm going to call it AA here, acetic acid. And how much I need from that? So what's the math? What is my XML? 333.3, right? Milliliter. So I take this amount, again, put water, put this in, and then make up the volume. I have now 1 liter of 1 molar acetic acid. Great. Then I go and prepare 1 liter of sodium acetate. So if I want 1 liter of 1 molar, then I go back to my molarity equal number of moles per volume and number of moles equal mass over molecular weight. So I want 1 molar. So that means 1 mole per liter. So this is 1 here, moles per liter. So mass is what I'm looking for. And molecular weight is 82 grams per mole. What would be the mass in grams? 82, all right, 82 grams. Okay, so thank you, Madison. So 82 grams. In this case, I also dissolved in a little beaker before, and in any amount of water, I dissolve my 82 grams, 200 milliliters of water, whatever I know about the saturation, and then I make up my 1 liter solution. All right, so now I have a liter from here and a liter from there. That's 1 molar solution. Great. Now I want to know how many milliliters of this do I mix with how many milliliters of the acid and base to mix together to give me 1 liter of 1 molar.
Would be 408 milliliters of base.
Yeah.
590.
Thank you. Yes. 408 milliliter. How did I do that? Instead of 1 here, I did, okay, I don't know where you can see, let me do it over there. So I had 1,000. No, I have an A minus, I'm solving now. And here I have 1,000 milliliter instead of 1 molar, I'm using a volume, minus this one equal 0.69. Mole, yeah, mole. Whatever it is. So now I'm solving for A minus, so A minus would be 408 milliliters. And then HA is 1,000 minus 408 equals the 592 milliliters. So I get my volumetric class. I add this, I add that, and now I have my liter of 1 molar because I standardized the molarity of the 2 solutions. And then I just combine the volume to the final volume that I want. Now we're not done. You just take that solution, measure the pH, so you do in the lab next week, and determine if you adjust the pH to the final pH that you originally attempted.
So the first way just kind of skips the standardizing and just goes straight to the buffer.
Yeah, exactly. You go straight to making by determining how many moles you will need of each. Look at that, we're right on time. And you can take a picture of this. You can come up to me if you have questions. And guys, just a quick note for next week, you already have all the information you need for the lab. We have quiz requires calculation, so please, if you have questions Saturday maximum, not Sunday, so that we can help you. And next week, we're gonna start with an overview, the best topic in the world. Oh, yeah. Don't forget to give me your calculation. Take a picture of it and give it to me for extra credit.
I just had a question.
Yeah.
The left. This is the
Let me just, I need to stop recording so that we're not recording. Okay.